Welcome back to another explainer brought to you by Forge College. I am absolutely pumped for today's session because we are diving headfirst into the really fascinating mechanics of Ethereum fundamentals. Specifically, we're rolling up our sleeves to build a custom cost calculator and actually run a live transaction demo. So, let's jump right in. Now, I've got to acknowledge the slight context whiplash we might all be feeling right now. In our last module, we were deep in the trenches installing Solana Cloud tools. Well, it is officially time to put away those Solana wrenches and pull out our Ethereum gas gauges. We're shifting gears from Solana's architecture straight into the mechanical beating heart of Ethereum's dynamic gas pricing. It's a completely different beast, but honestly, it's just as fun to tinker with. Here is the engineering blueprint for today. We'll quickly cover theory to reality, the calculator blueprint, firing up the node, running the demo, verifying the results, and we'll wrap up with what this means.
Starting with Section 1, Theory to Reality, Automating Cost.
Up until now, we've really just been relying on abstract paper calculations, but to build an executable automated calculator, we have to feed it the exact right definitions. The effective gas price is simply the sum of the base fee and the priority fee charged by the miner. The base fee is basically what the network demands to process your transaction, and the priority fee? Well, that's your tip to get it done fast. This is the core addition problem our tool has to flawlessly solve every single time. And that brings us to our critical multiplier, gas used. This is the actual amount of computational effort consumed by a transaction. Now, the absolute crucial thing to remember here is that gas used isn't just a static, predictable guess. Internal contract logic, hidden loops, or even unexpected gas refunds can totally alter this number on the fly when the transaction executes. Our calculator needs to handle real observed data, not just hopeful estimates. Moving on to Section 2, the calculator blueprint, hands-on setup. Okay, it is time to sketch out the mechanical schematics for our local development environment. Think of this like setting up your engineering workbench. First, you need Node.js installed. Make sure it's version 16 or higher. Then, you'll create a folder and run npm init-y to set up your package. Next up, we install Hardhat and Ethers, which together make up the foundational engine of our Web3 setup. Hardhat is our local testing laboratory, and Ethers acts as our communication cable. Finally, we just initialize an empty Hardhat config. Follow those exact sequential steps, and your engine is primed and ready. So the real secret sauce here is how we organize our logic. We're creating 3 distinct files in our project directory to keep everything incredibly clean. The feeCalculator.js handles pure computation, so absolutely no network calls, just raw math. Then txDemo.js handles the actual node execution, actually sending the transaction. And finally, last run is a JSON tracking artifact that records our inputs and outputs. By strictly separating the math from the network calls, we can isolate and squash any bugs so much faster. Inside your feeCalculator file, you're going to write a compute function. And the logic here is basically the golden rule. The effective gas price equals the big int of the base fee in Wei plus the big int of the priority fee in Wei. I literally cannot emphasize this enough. You must strictly use integer arithmetic. We wrap these values in JavaScript's big int because, frankly, regular JavaScript numbers simply cannot handle the massive scale of Wei without completely losing precision.
And speaking of massive scale, just look at that number. 1 quintillion. That's a 1 followed by 18 zeros, representing 1 E18 Wei, which perfectly equals 1 whole ether. Floating point conversions in JavaScript are a notorious, frequent source of disastrous errors in Web3. If you try to do decimal math with this number, JavaScript is going to round it off, and you will literally lose money. So always use big int.
All right, Section 3, firing up the node, local JSON RPC.
We have our files ready, our blueprint is drawn, and our big int math is locked in. Now we turn on our local test environment. By simply running the command npx hardhat node in your terminal, the magic happens. Hardhat instantly spins up a local JSON RPC endpoint at this local host address, completely equipped with a list of pre-funded test accounts holding imaginary but mathematically perfect ETH. It's your ultimate safe sandbox.
Section 4, running the demo. txDemo.js, execution. So our node is humming away in the background, and we are ready to execute. We'll use our script to send a simple 0.001 ETH transfer between test accounts and capture the printed JSON receipt. Notice just how sensitive the final cost is to your priority fee adjustments. In both the low and high priority scenarios, the base fee is identical, and the gas used is fixed at exactly 21,000. But simply by bumping the priority fee to get processed faster, our total expected cost jumps from 23 trillion Wei to an incredible 63 trillion Wei. The math scales so aggressively, which is exactly why calculating this precisely is vital.
Section 5. Verify results, static versus actual.
This is the true moment of truth, where we feed our observed JSON receipt back into our calculator. Now, you might experience a little bit of whiplash here. Seeing your expected static calculation diverge from the actual blockchain receipt is basically a developer rite of passage. This happens because the node's state is completely dynamic. The base fee might have ticked up by a fraction of a percent in the split second between your estimate and the actual execution, or maybe a minor contract refund changed the gas used. Remember, the actual receipt is always your ultimate source of truth.
If your calculator's totals failed to match the observed JSON outputs, hey, don't panic. Just run through this rapid-fire troubleshooting checklist. Number 1. Did you actually use Big Ant for all your math? 2. Did you use the receipt's effective gas price instead of just the pending base fee? 3. Watch out for those sneaky off-by-1 errors. Make sure you append .toString when pulling from big number libraries. And finally, double-check that you are actually targeting your local node and not accidentally pulling the live Ethereum mainnet.
Once your calculator passes that verification checklist, I actually have a challenge for you. Your scenario goal is to document 2 specific dynamic pricing scenarios that prove your script can catch meaningful variations. I want you to tweak your code to create a greater than 20% total cost change simply by increasing the priority fee relative to the base fee. Run it, log the JSON, and let the math prove that massive percentage difference for yourself.
And finally, Section 6. What this means, key takeaways. Let's wrap up with the ultimate takeaways from our successful engineering experiment. We proved 3 core principles today that really formed the foundation for gas optimization. Number 1. Always perform integer arithmetic using Big Int to avoid precision loss. Number 2. The actual transaction receipt's effective gas price is your authoritative truth, not your pre-transaction estimate. And number 3. Small changes to the priority fee can cause absolutely massive percentage differences in your final cost when that fee makes up a material share of the price.
Which leaves us with a pretty provocative question. Knowing how wildly a small priority fee tweak can inflate your final Wei totals, how much do you think you've been overpaying for your transactions on mainnet? It really makes you rethink exactly what happens when you hit that send button, doesn't it? Well, that sets us up perfectly for our next lesson on advanced cost scenarios. To dive deeper into this subject and explore other amazing Web3 topics, be sure to visit forge.college. Thanks so much for joining me on this explainer, and I'll see you in the next one.